myself. Optimal estimation is probably the most theoretically developed approach for both the setter for retrieval, also for inverse modelings. In our atmospheric community, in doing retrievals, initially it has been mainly used for profile retrieval, but now we have seen getting more and more popular even for doing the aerosol and the cloud retrievals. And so my talk has two parts. So the first part is talk about optimal estimation. Then the second part is talk about its application to the ozone profile retrieval from the satellite UV measurements. Here I list some recommended readings, especially for the students. If you really want to use the optimal estimation, or for my case, if I need to give a lecture about that, then one must have, that's the largest book, the textbook. I think you must have that. Before I am given lecture, I try to search the internet to see if there's some materials available. I found some online lecture material about the optimal estimation. There's another talk about that, about the inverse theory. So I have stolen some material from this lectures. Here are two references to describing our ozone profile retrieval algorithm to retrieve ozone profile from GOM and OMI. At the end, I list four the latest papers to retrieve CO2 from the GOSAR data. So this paper from 4 different groups. So we can, if you are really interested, you can look at this paper to see how different groups using the optimal estimation, but in different implementation in terms of details, how to tackle the same problems. Outline here. First, I talk about inversion problem and why we need the optimal estimation. Then talk about the methodology, the tools to do retrieval characterization, like Ivan kernel vertical resolution. How to characterize detailed error analysis using the optimal estimation framework. Talk about some of the practical implementations. Then I show some one single slide about comparison of the optimal estimation with the least square fitting. Also, another widely used approach is called the Tikhoff regularization approach. Then talk about our OMI GOM and the OMI ozone profile retrieval. So this is a chart describe our remote sensing observations. So here we measure the radiances from 2 different frequencies. So this is the thermal emission. And the measurements is related to the actual vertical profile because this species have different absorption depending on the pressure and the altitude. So due to the interaction of the absorption from different layers, we get this. So which can be described in this equation. So the y, that's the measurement vector, m element. So this is the epsilon, that's the measurement noise. And we have the f, that's the forward model, which tells us about the physics. Yeah, sometimes it's more than the radial transfer model. And the x is the target of our interest. That's could be the ozone profile of n elements. Could be some additional parameters. B, this is another parameter which is used in the forward model, but might not be in the state vector. Because the remote sensing observation provide indirect measurements, we didn't measure the x directly. So that's why this is called inverse problems. And in order to get x, it looks like we just want to get the inverse of the forward model. but in reality, we might not be get the inverse of this formal model. It might not be unique, or it's very difficult to evaluate. So that equation can be linearized about x naught and y naught in like this. So this is the k. This is the weighting function matrix. It's a derivative of the formal model with respect to the x. So in this system, if you have more, if you have less equation, you have more unknowns, then the system is underdetermined because you have more unknowns. But typically, we have a lot more equations. Then the unknowns, it's like overdetermined. But in reality, because not all the equations are independent, they are kind of relate to each other. So in most of the conditions, it's still underdetermined problems. Just consider a simple linear case. Assume the x naught, y naught is 0. Then we can have this equation. So, and also assume m equal to n. Then we just need to inverse this k matrix. Does that just solve the problem? Oh, by the way, this is just a synthetic set of weighting function matrix from Roy's book. So this is a typical ladder sounder measuring the thermal emission. This is another figure from Roy's book. I think the quality is poor because I took it with the iPhone. So just look at this example. So the solid line, that's the original. That's the original profile, and the B, the dotted line, that's the retrieval, exact retrieval. Assume there's no noise. We have perfect measurements, and you can see it agrees with the original profile quite well, but you can see there's a very large difference. That's because the measurement does not have enough information to resolve this profile, especially in the upper part of the atmosphere. And if you look at C, this is the exact retrieval, but I'm including a very small noise. It's about 0.5 K in the measurement. And you can see the results becomes very different from B, because that's because small errors in the Y can cause large differences in the retrieved X. So this is called the noise amplifications. So in a lot of conditions, we don't, especially for profile, we don't have unique solutions. The solutions are often unstable and a lot of times meaningless. Just talk about the nonlinearly square fitting, which is probably the most widely used inversion technique. Kate just mentioned those both. Both use this for inversion. Typically used if there's more equations than the unknowns. So here we're trying to minimize the difference between the measurements and the formal model with a cost function like that. Here we're trying to weight different measurements according to the measurement covariance matrix. In practice, this measurement covariance matrix often assume just diagonal because it's often we don't have good knowledge about the correlation between measurement of different wavelengths. For this nonlinear square fitting, we often just assume it's assume this as an identity matrix. Just treat every wavelength equal, which is a very good assumption for a lot of cases. Again, it's not suitable for profile retrieval because of non-unique, unstable, meaningless solutions. So we need to find some extra information to get stable and meaningful solutions. So that's we need the optimal estimation. So optimal estimation is the Bayesian's approach to the inversion problem. According to the Bayesian's theorem, which states that how different pieces of information can be combined together using the probability theory, assuming the Gaussian distribution. So the PDF stands for the probability density function, so which is Gaussian, can be described by the mean value, also the variance of the distribution. According to this, so this is our goal. So this is given a y, given a set of measurements, we want to find the x. So this is called the a posterior PDF of. So it's related to. So this is the likelihood PDF. So this is given x. What's the possibility of the y? So this is mostly from the forward model, also from the laws. The px, that's the a priori PDF, describes the knowledge, the state of knowledge for the x can be described by the a priori, also the a priori covariance matrix, and the y, the py, that's this the state of observations before it was made. So what's optimization? So it's basically to optimally combine the a priori knowledge with the information available from the measurements to derive an optimum estimation. For the linear problem like this, the cost function is like that. So basically it's similar to the nonlinear least square fitting in the first part, and we have addition term. We're trying to minimize the difference between the retrieved and the a priori, simultaneous with the difference between the measurements and the forward model. If you go to the Rice book, you can derive a solution just based on the probability theory. So this is the solution to that. In this equation, everything can be known. We can solve the problem just using the matrix operations in IDL, in MATLAB. But in practice, it's computation expensive, especially to solve the inversion of this matrix. So in practice, you often use the single value decomposition approach to solve the problem. You can read the Rice book about this. Also from the PDF, from probability theory, we can derive the a posterior error covariance matrix using this equation. In a lot of the conditions, the problem are nonlinear, and the equation can be linearized around. So the retrieval process is kind of iterative. So we can reformulate the problem, linearize the problem around our previous iterations, like that, and then we can slightly change the cost function here just to minimize the difference. This is so basically you try to minimize the difference between the delta x, also the delta y. To solve this, can be for typically weakly or moderately nonlinear problem, we can solve this using the Gauss-Newton approach to give the solution. This is just the same solution, but in different forms. But if the problem 2 is strongly nonlinear, we might not be able to use this approach because the previous solution might be too different from the actual optimal solution. So we often use the Levenberg-Markle method to tackle the problem. So basically, we are trying to use the deepest descent scheme by adding some matrix, scanning of identity matrix, or some just diagonal matrix, or for the operator estimation, we often use a scanning of the actual a priori covariance matrix. So the solution is still very similar. Just the only difference, we add this gamma here before the a priori covariance matrix. So initially, it could be a large value, so then the solution is stable, at least because it's very close to the a priori. Ideally, you want to find the optimal gamma at every iteration, but which is very expensive. So in reality, in the Rossberg give a strategy, describe the strategy to approach this. So initially, you can assume any gamma, something like 10, and then you evaluate the change in the cost function. So if the ratio is the change is greater than 75%, then you can reduce this value by some factor of 2. If the ratio change is smaller, then you increase this value. Otherwise, just don't make any change. If this gamma becomes very small, then use 0, then it becomes the same solution as the optimal estimation. The nice thing about optimal estimation is provide a very nice tool to describe the retrieval. One of the most useful information is the Avni-Kernel matrix, which is by definition, which is the retrieval sensitivity of the retrieved state to the change in the actual true state. So here is just an example of the Avni-Kernel from our own profile algorithm. So here each line is a row of Avni-Kernel corresponding to attitude. Another very useful quantity is called the contribution function, which is defined as the sensitivity of the retrieved state to the actual measurements. So this is a very useful quantity, often used for error analysis. From the Avni-Kernel matrix, we can derive some simpler quantity, for example, like the degree of freedom for signal, which is or total DFS. That's the trace of the Avni-Kernel matrix, which indicates the number of independent pieces of information from the measurements, and the diagonal elements at each layer. We can also call that DFS at each layer. But it should be noted that the DFS not only depend on the physics, which is the K matrix, but also depending what kind of a priori covariance matrix you assume, and what kind of a measurement covariance you have. So with this Avni-Kernel, actually you can relate the retrieval to the true state using this equation. So basically the retrieval is depending on the a priori, convolved with the Avni-Kernel to the difference between the true state and the a priori, with some retrieval laws. So this equation is very important. Is very important for, especially for doing a comparison validation. Often we want to compare. For example, we have a high resolution open sun observation, and we want to compare with our GOM retrievers. So typically, we want to convolve the high resolution data with the Avni-Kernel using this equation, so that we can compare the profile at the same kind of a resolution. So in this way, actually, we remove the smoothing error from the open sound data. Another important quantity is about the vertical resolution. So we have heard a lot about vertical resolution, which is a quantity derived from the Avni-Kernel. We have many different definitions, but the simplest is called the width, the full width at half maximum of the rows of average kernels. So like of each line, maybe you can define a 4 width and a half maximum. But a lot of cases, it's very difficult to find the 4 width and a half maximum because the average kernel can be dislocated. For example, so this is for 9.7. So that's the yellow line. Probably it's not clear. Ideally, we wanted to pick at 9.7 kilometer, but here you actually pick at near the surface. Also, often it has some very large positive or negative lobes. It doesn't have a well-picked. So in this case, we cannot define a 4 width and a half maximum. There's some other quantities. So one example is the Backus and the Gilbert spread, which can be described using this function. Another, they call it the resolving length, which is defined as a spread around the center. Another thing is that we can use the upper estimation formulation to do a very good error analysis. For given a retrieval, the difference between the retrieval and the true state can consist of many different kinds of errors. For example, if we know the true state, we can estimate the smoothing error because we cannot resolve the vertical profile or vertical distribution with the true state. We have full model parameter error, like the full model calculation might depend on temperature, but we don't have a good logic about the temperature. And we didn't retrieve that in the temperature. That can cause some error in the retrieval. Like a full model error, for example, we are using a V-light dot. Ideally, you want to use 20 streams, but that's too expensive. So maybe we can just use 6 streams, which can, of course, can induce some error to the calculations, which can propagate to the retrieved profile. We have a systematic error in the measurements, because it's not accurate. We have some calibration problem, which can also cause error in the retrieval. We have a retrieval noise. So this is for a single case, but a lot of cases, like the smooth, I just talk a little bit about smooth error. Smooth error sometimes can be considered as an error, sometimes is not an error, depending. So if you say I'm retrieving a smooth function of the true state, then in this case you don't have to consider the smooth error as an error. But if you think you are retrieving the true state, then smooth error should be considered as an error term. Because a lot of conditions we don't have the true knowledge about the true state, so we cannot derive the actual smoothing error, but we can derive the error in a statistical sense. So we can derive the smoothing error covariance matrix according to this equation. But it should be noted that to derive this, you have to use the covariance matrix of a real ensemble of the states, which means you have to use the climatological a priori covariance matrix. It also for formal model error, if it's not systematic, it's kind of random. We don't know the actual error in the temperature. We only know the kind of Gaussian distribution of the error in the temperature. Then we can also use this equation to derive the formal model parameter error covariance matrix. We can do the same thing for to estimate the retrieval noise. We already mentioned about the solution, the S posterior solution error covariance matrix. If we use the actual a priori, the climatological a priori covariance matrix, then the solution error is equal to the sum of the loss error covariance matrix and the smoothing error covariance matrix. Talk about a little bit about the practical implementations of operator estimation. So we have a lot of this is our main input. We have the observations, we have the measurement noise forward model, we can derive the K matrix from the forward model. We have the a priori covariance matrix, well, somehow we have an issue. So the y, the vector could be the radiances or could be normalized. Sometimes you can take the logarithm of the either radians or normal radians to make the problem more linear. For the measurement covariance matrix, we often assume that it's uncorrelated diagonal due to the lack of knowledge of the off-diagonal elements. And sometimes we don't even have a good knowledge about the measurement error for each individual measurement. For the state vector, like for ozone, could be partial ozone column, could be mixing ratio, could be logarithm of the mixing ratio, so that you can always get a positive retrieval. It can contain some additional parameters. Often the retrieval state could be different from the actual full state used in the Ford model, like an ozone profile. If you want to do a very accurate calculation, you might want to use 100 layers, but computation is expensive, and you don't have that much information. So you might just retrieve the state at 24 layers or 10 layers. And so then you have to map between the full state and the retrieved state using some matrix. You have to map between the actual K matrix to the actual to the K matrix used in the retrieval. For form model, it could be radial transfer model, could be lookup tables of the radiances and weighting function. In our own profile, we have to include other things which can be modeled with the Wheeler-Edwards transfer model. So for some parameter, we have to use a Physics difference to derive the weighting function for those parameters. So for the Jacobian matrix, it has to be consistent with the definition of y and x. This somehow we can make a mistake because we just use the Jacobian matrix directly from the radial transfer model. So we have to do some transformation to be consistent. For the a priori, that's the logical state before retrieval. According to Rogers, we cannot use a retrieval from a previous iteration as the a priori. We cannot do that. Then that's not optimal estimation. It's mostly derived from climatology, but could also be derived from the model simulations. So also for the a priori covariance matrix, typically we cannot use the full covariance matrix because it can cause a numeric problem. Often we just use the a priori error, then we can construct our a priori covariance matrix using some equations like this. About the initial could be the same as a priori, but could be different. We can, in practice, we often use the retrieval from a previous or adjacent pixel to speed up the convergence. So because it's for nonlinear problem, it's an iterative process, so we have to determine how to stop the iteration and terminate the retrieval. There are different criteria. You can, for example, you can define based on the threshold in the relative change in the cost function or the relative change in the state vector or in the fitting residuals. You can combine several criteria to determine the convergence. So the keys to the retrieval to the optimal estimation. The first, you want to have, of course, you want to have the accurate wavelength radiometric calibration of the measurement, so which is a key. Also, you want to have the accurate formal model simulations, the algorithm physics. Of course, you don't need to make it too complicated for you purpose, but you want to make it accurate enough for what kind of objective you want to retrieve the actual profile. We want to have a good a priori logic. We want to use the best a priori logic available. Sometimes we want to have a very good logic about the measurement error, which is often neglected, but actually it's very important. I'm going to talk about more detail based on our OMI and GOM own profile retrieval algorithm. Here I want to compare just one single slide. I want to compare the differences between the least square and opera estimation and the Tommy or Phillips-Tikhonov regularization. So this is a cross function. So this is the opera estimation. If we just remove the part related to the a priori information, so then we have the least square fitting. For the Tikhonov regularization, basically we don't use the a priori covariance matrix. If sometimes because it's not available, then we just use adding some smoothing constraint to which is often like the zero derivative or the first derivative or second derivative of the actual profile. This actually is getting a lot of applications in the retrieval. Often used if there's no good logic about the a priori covariance matrix, or sometimes you want to maximize because it doesn't use the a priori. Because it doesn't use the a priori information, so you can give more degree of freedom for signal. If somehow you want to maximize the degree of freedom for signal from the measurements, you can consider this approach. But then you have to determine this is called the regularization parameter. So you have to use other minimization procedures to determine this approach. For one of the examples is the error curve method. The solution, again, they are very similar mathematically. If you just remove the x sub a from the opera estimation, you get the solution for this least square fitting. And you replace the a priori covariance matrix with this, you get the solution for the Tikhonov regularization. But then you have to determine this parameter. The main purpose of this slide is that since we have very good theoretical framework for optimal estimation, I want to emphasize we can use this similar concept like the Avni kernel contribution function. Or if we want to carry out an error analysis, we can use this theory developed for opera estimation for this kind of approaches. Let me talk about the second part about the opera estimation on profile retrieval from the UV measurements. Just give a little bit of background about that. The measurement of the own profile was started in 1929 using the remote sensing Omega approach, also from Owen Sound in the 1960s. From satellite, in 1957, Singer and Wentworth proposed to derive Owen profile from backscatter UV measurements from satellites. This idea had been realized from a series of BUV, SBUV measurements to measure the profile, vertical information, but mostly to above 20 to 25 kilometers. Although we can measure the total ozone below 25 kilometers very nicely. That's an old paradigm, especially in the last century. The BUV technique cannot measure ozone profile below the dense peak, could not separate the stratospheric ozone from the total ozone. And since in 1987, pioneered by Fishman and Larson, they have proposed to derive the tropospheric ozone from the total ozone, also some stratospheric measurement like SAGE. A lot of groups have developed this kind of a residual-based approach to give us very useful information about the distribution of tropospheric ozone. I will not go into detail of this different method. Professor Jack Ham, but I don't know which Jack Ham, have actually involved four of the methods. But there's some limitation with this method. Mostly most methods can only derive the month's mean, the tropical ozone column, many in the tropics. But with improved instrumentation like OMI and MRIS on the same platform, also improved methodologies, we can derive the tropical ozone on a daily basis. But we still, with large uncertainty, like 4 to 8 Doppler units, even you have perfect, OMI and MRIS at the same places. Of course, you have some interpolation error. Kelly mentioned in a study in 1997, Kelly mentioned conduct a sensitivity study that it's possible to extend the retrieval to a troposphere from backscatter UV and visible measurements. Let me just talk about the principle of this BUV retrieval. And so the interaction between the sunlight with the ozone in the atmosphere, also interaction with the clouds, the surface. So this is the ozone cross-section as a function of wavelength. You can see this. I have a plot in both typical scale or the log scale. You can see the cross-section varies by 4 or 5 orders of magnitude. And in the Hawkins band, you have a lot of structures here. So the interaction of this gives you a measurements like this. Again, you look at the scale, it varies by 4 orders of magnitude in the radiances. So these have very important implications about retrieval, also about the measurements, because the radians are often, because the range is too dynamic. So the radians are often made in different channels. You probably didn't see much structures. So the measurements are subject to wavelengths and the radiometric calibration errors, especially for these shorter wavelengths. And you have different offset in different channels, so which make the retrieval very challenging. Here I'm showing I'm plotting the normalized photon pathness. Actually, just the same as the MS factor. It's normalized as a function of the altitude, also wavelengths. You can see that at short wavelengths, it's blank, which means there's no photon penetration because the ozone absorption are too strong. There's no photon penetration even to below 40 kilometers. But with increasing wavelengths, the photon can penetrate to the low troposphere, and above 300, some photons, a limited portion of the photon can penetrate to the surface. The low panel is the vertical gradient of this figure. Actually tell you about the vertical information. So you have some vertical information in the stratosphere, you have some vertical information in the troposphere, but it's relatively weak in the UTIS region. So basically, the vertical the information comes from the wavelength dependent on photon penetration because of the property of the ozone absorption cross section, and also we can get additional information from the temperature dependent Hawkins bands. The same principle has been applied to SO2 retrieval to derive the height information. In the SBUV retrieval, because it does not provide vertical information in the troposphere because we only use too few wavelengths. Also, the poor signal to loss ratio due to kind of special NAS because the the different wavelengths are not looking at the same thing. So there's some error due to that. You can mention the series of UV visible spectrometer. We have also mentioned about GOM, which is the first one to make hyperspectral measurements, starting in 1995 with a moderate, with actually quite a good resolution, but with a poor spatial resolution. For ozone profile trio, we often have to do a lot of co-adding because different channels have different spatial resolution. For ozone profile retrieval, it's a line 60 kilometer by 80 kilometer square. Yeah, for ozone, for OMI, we have slightly worse spectral resolution, but we have much better spatial resolution, and we have daily global coverage. When I first get started at Harvard Smithsonian as a postdoc with Katie, my first task is to derive ozone profile from GOM data. At that time, we already have 4 physically based ozone profile algorithms. 3 of them are based on optimal estimation, and 1 are based on the Tikal level regularization, which are listed here. But you can look at, if you look at that, different algorithms, different groups, these are different spectral region, and you have to perform calibration correction or empirical correction to different measurements, and the approach are different. At that time, I think the robust determination of tropical ozone information have not been demonstrated because of some challenges. The first one is that it requires consistent and quite accurate absolute calibration. Also, in order to get information, the tropical information, you have to fit the measurement to at least better than 0.2 to 0.3%. In order to extract the weak tropospheric ozone information. Also, 90% of the ozone above the troposphere. When I first get started, we actually tried the Tikal level regularization approaches. We implemented that, but it doesn't work quite well. Then we switched to optical estimation. So now we have developed the ozone profile retrieval from both GOM, OMI, GOM2 data, and we have demonstrated we can get some valuable tropical ozone information. Although still quite challenging. I think there's still a lot of challenges for this problem. Here just first show some pretty pictures. So here I'm showing an orbit of a retrieved ozone profile from GOM. So they are retrieved at 24 layers. And here, this red line, that's the tropopause. So we can see the vertical distribution from the South Antarctic to the Arctic region. And here you have the ozone hole. Here you can see the ozone maximum just outside the polar vertical region. In the tropical regions, you can see enhanced ozone in the southern mid latitudes. Also over the Indonesia region, which is caused by biomass bowling, due to the largest or Leland event in the last century. Here, just a global map of the tropical ozone, column ozone, even with a line 60 by 80 kilometer kind of resolution, we can still derive a very good, a distribution of the tropical ozone from GOM data. So if you look at the tropical region, you can see the enhanced ozone over the Atlantic, also over Indonesia region. Even though we're using the zonally invariant air power information, but we can certainly see the longitudinal distribution of the ozone vary from 9 Dobson units in the Pacific region to more than 60 Dobson. So which demonstrate we certainly have the information from these measurements about the tropical ozone. So here just more example from OMI. So this is just based on single day of data. So this is total ozone column. This is the tropical ozone column. This is stratosphere ozone column. Here is the tropical ozone profile for the tropical region. We can see ozone maximum in the peaks in the South Atlantic region in the middle of troposphere. So this is the vertical distribution in the troposphere, but for the middle latitude, you can see we don't have enough vertical resolution, but we can certainly see some enhancement could be from the stratospheric intrusion. Certainly we don't have enough vertical resolution to separate from the stratospheric intrusion, or maybe some enhancement, so we have to do a very good analysis of the data. Let me talk about the retrieval algorithm. So it's a compilation with the spectral fitting, which Katie had talked about, with the rate transfer model, then use the opera estimation inversion technique. For fitting window, it's different from GOM and OMI data, also GOM2, because of some of the calibration problems in the data. Right now we retrieve ozone profile at 24 layers, but which is very easy to adjust. Again, it's a year post problem, so we have to use some a priori climatology. Right now we have used two kind of climatology, one is the monthly mean and the zonal mean climatology based on the megapeters. And then recently, Sunny Park from Pusan National University have developed tropopause-based climatology, which we have used to significantly improve the retrieval in the UTIS region. I'm going to share 2 slides about that. And so, just show you some example about the effect of a priori on the retrieval. So this is the a priori based on the zonally mean, zonally invariant megapeter climatology. I think this is at 200 millibar. This is over the I forget this which region. And this is the a priori the climatology tropopause based. It's derived from the tropopause. Us combine the tropopause information from the global forecast, the model, with the climatology, then we can derive this kind of a priori information. So this is the retrieval. This is using this climatology. This is using this climatology. We can see using this climatology can capture much better the horizontal gradient in the UTS region. Just look at the cross-section profile for this segment. So this is from the megapeter climatology. This is from the new climatology. We can resolve much better the vertical structures here. So this is the retrieval. We have a lot of smoothing here. We have better clean separations. This is the a priori error from the old climatology, from the new climatology. We have much better a priori information, especially around the UTS region. So this is a retrieval error. We have a small retrieval errors by using the new climatology. So we did some evaluation with own sound observations. So basically you can see the relative from the new climatology. I'm showing the mean, the mean biases. Oh, this is the standard deviation. Oh, so the up panel is for the mean biases, the lower panel is the standard deviation of the differences. We can certainly, by using this climatology, we can significantly reduce the mean biases, also the standard deviation in the UTS region. We use the V-LiDAR, but then we have to perform some correction with lookup table for polarization or for GOM. We switch to do some online correction at some select number of wavelengths for OMI. For reinfect, Katie mentioned about reinfect, and we, I guess, first get started with the reinfect estimate using Katie's model, but then we find which is not enough for ozone profile retrieval because it doesn't account for the effect of reinfect, the dependence on the ozone temperature. So we switched to use this reinfect model developed by Sir Aris and Evans. Basically model the first order of the rotational Raman scattering using a single scatter model. We also use the GOM OMI solid irradiance as a source function. Based on this, we can significantly reduce the fitting residual, especially in the Hawkins band. We have to use derived sleep functions to convert with a high resolution cross-section, we have to perform additional correction for the solar, it's called the solar, 1 minute? Okay. So we have to spend a lot of time improve the algorithm physics for clouds, aerosol, surface albedo, using some auxiliary information for temperature, surface pressure. We also simultaneously fit other trace gases. You also need to do a good job, especially for GOM. You have such a big pixel. You have to do a good job estimating the viewing geometry. Just show you quickly the importance of the cross sections. So here, just comparing the fitting residual using different cross section. By using the BDM, the Brian cross section can give you a much better fitting residual. Recently, we do the same exercise with GOM data. Just try different own cross section. The BDM cross section, also the recent high resolution cross sections. Even though they give a very similar fitting residual, but if you look at the mean difference for a single orbit, the difference could be up to 20 to 40%. So it's very sensitive to the own cross section. So basically, we have to go through evaluate each cross section available to find out the optimal, the best cross sections. 1 minute. Katie mentioned sleep function for GOM. It's a very significant wavelength dependence. So you have to account for that very well in the retrieval algorithms. Calibration, this is for OMI. So we try to do some empirical correction. Here I show the correction as a function of wavelengths, also for different cross-track positions. For GOM data, especially after 2000, you have lots degradation. It's huge. Here I'm showing the degradation as a function of time, but for different wavelengths, it's up to 25%. It's huge. So you have to do some correction for that. So here, because we have to use not only radio transfer model, we have to use so the measurement vector, the definition of the measurement vector is very more complicated. It's not just directly out of the wave dot. So you have to make some transformations. So this is a static vector. We have to include other parameters. This is just an example from OMI. Just mention about measurement error. Typically, we use the random loss error from the data. But for OMI, recently we have to assume some flow error, which is, if the error is smaller than that, 0.2%, then we assume it's 0.2%, just to stabilize the retrieval, but significantly reduce the DFS. So here, this is a fitting residual average. This is from one object of GOM data. You can see the fitting residual is about 0.1% level. So that's why we can extract trap's own information from the OMI data. I think I'm going to stop here. Maybe this just uses the operator measure formulation work to do detailed error analysis, not only for profile, also even for the trap's own column, the total column. This detailed error analysis, using a tool from optimal estimation, you can do a detailed error analysis. So this is just an example from GOM. Even though we make a lot of progress, but there's still a lot of work to do. I think it's still a very challenging problem. One of the two main challenges we want to work on, just briefly mention that. So we want to reduce interferences from the surface albedo aerosols. We plan to use longer wavelength range to improve the knowledge of the spectral dependence of the surface albedo. Aerosol cloud, we want to improve the characterization of the measurement and loss error. We're thinking about explore, maybe going back to T-curve, regularization, but with some improvements, trying to maximize the tropospheric information. Yeah, I'm going to finally stop here.
Thank you very much. Great lectures. We can take one short question.
I thought you should not have questions.
Temporal and sensor will measure the hourly measurement, but also optimization methods also need very accurate upload data. Also, ozone algorithm need very close section. Close section also dependent on temperature. So I'm thinking about we need hourly temperature profile or hourly radiation, hourly ozone data. So it is not easy. So maybe could you give a comment about hourly?
For the temperature field, I think we can use the meteorological data. We have a lot of meteorological forecast data, which can be used.
Hourly?
Yeah, I think it's hourly or even at a higher frequency. Yeah, but we to improve the retrieval, we want to use those on the real-time basis for operational retrieval. Yeah, which might be challenging. But the air priority, I think we have a good air priority based on the work you have done. So.
To use these parameters, we need hourly dependence on the tropical state.
Yeah, ideally, again, can be derived from the meteorological data. Yeah, but if we don't have that, that's fine. Then we probably the retrieval might not be that accurate. Could be less accurate. But that's not a keening issue, I think.
You can ask questions during the break. Let's have a 5-minute break.